discussion on spatial regression models. So the SARMA model, you'll remember, comprises of two terms. The SARMA model takes this form: y is equal to beta x plus lambda wy, this is the autoregressive term, and mu wu, this is the moving average error term, spatial error term. As I had told you in the class on Monday, this type of SARMA model assumes spatial homogeneity. And this assumption of spatial homogeneity is reflected in a constant value of the coefficient vector. Now, it is possible to relax this assumption, and one possible way of doing so is to estimate a geographically weighted regression. GWR in short. In a GWR, beta depends upon the coordinates or on a particular location. So it is basically a local regression. Depending on if you have k number of points or k number of regions, then you will end up with k number of equations. So this is very complex, and it leads to a lot of problem. How to interpret the different coefficients, analyze them, how to assess whether they are statistically significant or not, and a much simpler approach which can be easily interpreted and which any econometrician, basic course in econometrics covers it, is through spatial regression, spatial regimes. So spatial regimes basically looks at what we call structural stability of the regression model. So the association between y and x varies not across all the units, as in the GWR. It varies across regimes. So what happens is, if we have, let us say, k number of regimes, k number of regions, we cluster them into a smaller subset, into small groups. So instead of k, we have a smaller number of groups. Let us say we have 5 groups, 6 groups, not too many, and we estimate regressions for each of them. So it's basically it's some sort of a GWR, but whereas the GWR is estimated for each region, here we club together some of the regions, we form clusters, which can be contiguous or it may be non-contiguous. And then we estimate the regression model for each of these regions. So for instance, over here, we have different points, and the GWR the spatial regime model assumes that this green one has a particular set of coefficients. Alpha is 3 and beta is 2. In the pink one, the coefficient value changes to 4 and 3 respectively. And we have 5 clusters, deep green, black, pink, and we have 2 shades of blue. So we have 5 regions. So we get 5 regression models. For GWR, we would estimate regression models for each of these points. Now, how do we divide the clusters? For instance, over here, this is actually taken from a data. You can see that the data has been split into 2 subsets. One is south, so the blue is south, and the pink or orange one is 0, north, you can say, the remaining regions. And if you plot the kernel distribution, you can see that north has a much higher mean than south has. The distribution, the variance also is different. South may have a higher mean, but the variation is much less. South, on the other hand, has a lower mean, but you can see it has a higher variance. You can see over here that the blue distribution just goes on up till quite large values. On the other hand, the pink one is fairly concise. So in general, if we study the distribution and we find a bimodal distribution, or there are small peaks at the tail, at either tails, either over here. So we have small peaks like this, or small peaks over here. Then this would imply that we have spatial regimes. But there are other ways for doing so, which I'll discuss later on. So a spatial regime occurs when the variable of interest, for instance, stunting, etc., is characterized by distinct distributions in terms of different values of mean or variance for different geographic subregions. So we take the entire area that we are studying and we can divide it up into different geographic subregions, and each region is going to have a different mean or variance. I mean, obviously the mean and variance will differ, but the difference should be statistically significant. For instance, suppose we are studying crime rates, and we know that crime rates increases if the area is poor and if the population density is high. In other words, if a particular region has a lot of slums, then we would expect the crime rate to be higher. So if we do the brushing, then the exploratory spatial data analysis normally reveals a positive relation. Regions which are poor, which have a high population density, also has a high crime rate. But while brushing, suddenly we find that crime rate and population density has a negative relation. Well, one reason can be that as we are brushing, we move from a predominantly urban area to another region, a set of regions where urbanization levels are very low. So what happens is, in rural areas, it is the open space, less population density, where the crime rates are high. So you can see that there are two types of districts, one with high rates of urbanization, other points with where urbanization is low. And the relation between crime rate and population density varies across these two areas. So this is an example of a spatial regime. In the rural area, you have one regression with the coefficient of population density being negative. In urban areas, you have a different regression model, but now the coefficient of population density is positive. So is it clear, everyone? So in today's lecture, what we are going to do is we'll start off with an exploratory analysis and try to find out whether there's any evidence of spatial heterogeneity. So we'll first look at something that I think most of you have done, a test of a mean difference between regimes. So we have two groups. We divide the entire region that we are studying into two subgroups, and we find out the value of the variable in each of the two groups, and we simply test for the difference. This is the t-test or ANOVA. Then we will show how we can identify spatial regimes using brushing, and through scatter plots. Then, given the fact that we have identified spatial heterogeneity, how do we bring it into the model? So that will comprise the second part of our analysis, of our discussion today. So today we are going to go back to the New York City data, NYC data, and we have plotted rent in 2008. And you can see on the left hand side, we have a quantile map with 4 categories. And you can see that this is the Manhattan region. This has the highest level of rent, posh area. But overall, if you see, this area also, sorry, I should have made it broader. So these areas also have a very high population, high rental value. So overall, the rental values are high in this region. And this is brought out more clearly if you, instead of 5 categories, you form 2 categories. You can see very clearly that this region, this cluster, has very high rental. This cluster and another cluster over here. So if you can divide this New York data into 2 parts, you can find out there should be a difference in rent. So how do we identify? First let us focus on just Manhattan. Manhattan is this area. So how do we distinguish or identify Manhattan? The codes for sub-borough is 300 to 310. Now, at the bottom of this slide, you can see that this is the Geoda toolbar, and we go to this one. So from the right-hand side, the second one, besides between regression and the clock. So a window will open up and you have to change this. Normally, the first variable in the data set comes over here. So you have to change it to the variable of interest. And as soon as you do so, you will see that you haven't selected anything. That is why the the mean of rent is 0. And unselected means the entire data set. It is 1,257. It is given in the chart over here by this red. So 1257 corresponds to this bar. So you have the mean, the value, and the confidence intervals. So now you have the selection. For selection, you have to go to, if you remember, you have to go to tables and selection 2. And you'll have this window. So selection variable should be borrow sub, it's actually sub borrow. And you have to put in the quotes 300 to 310. Then you see that now instead of you can see that selected, this is Manhattan, much higher. The average rent is 2,062. And the remaining areas, the rent is much lower, about half, 1,078. And the null hypothesis of ANOVA is means are equal. So this is the ANOVA results. So the ANOVA tells us that the null hypothesis cannot be accepted. So in other words, Manhattan has a higher rental, significantly higher rental than the other areas. Now over here, sorry, I just closed. Any questions so far? Okay. Now, instead of choosing a particular district in using codes, we can also identify contiguous areas using brushing. So you know how to brush? You just press the left mouse down and drag it, and on the themeless map. And once you do so, the area will get selected. And automatically, this overrides the earlier selection. You can see that I don't have Manhattan over here. So for the selected region, red false, 1146. And for the unselected region, actually rent is higher. But look at the ANOVA results. Are the two means statistically different? Is the difference between the selected districts, rent in the selected districts, and the remaining districts, is the difference statistically significant?
No, sir.
So over here we see an absence of statistical significance. Now let's go back to the New York data. So we see that this is the area which has high rates. So actually this should be our selection. The earlier one, this was wrong. Now if we select this area, you can see that the rent 1507 and 977. And now the difference is statistically significant. Okay. So this is the first part, the simplest method. And let me illustrate this with Geoda, and then we can come back and go to the scattered plots. So let us see, this is New York. So I'm loading the data. Let me increase the map a little bit. Okay. So this is red. I come to averages chart between clock and red. So you can see that this is borrow sub, which is the first variable. So this is just this is a meaningless thing. So let us check the variable where is rent 2008. So the average rent is for all 55 observations is 1257. Standard deviation is 594. This is the average rent. Now, let me go to table selection tools. Okay, let me keep this, then I'll move it later on. So selection variable is borrow sub, and I make this 300, 310, and select all in range. So you can see that the Manhattan region is selected. And now let us see, this is, you can see Manhattan 10 borrows. The rental value is 2062. The remaining areas, much less. And these are the two rents. Sorry, actually, the problem is it's not showing. Manhattan is not showing let us say, so the maximum value is 1400. Let us make it how much? 2100. So you can see this is Manhattan. This is the unselected region, and this mean is for the all the 55 districts, boroughs. And this is the F test result. So let's close it and let's unselect everything. Just you have to click outside the theme map. So let us see. Let me start from here so that Manhattan can be selected. See, look over here, look at this side. Nothing has been selected. So that is why this is the rent for the 55 states. But look what happens over here when I select it. Nothing. Look, gaps are, look how the gaps are changing. See, as it is, let me make it higher. I don't need so much. So you can see that, look how the pink line is shifting. Okay, it's still statistically significant. But look over here, is it statistically significant? Look at the ANOVA results. No. I'm selecting another region, New Jersey, I think. Not much difference. So by brushing, you can find out the difference between, you can identify possible spatial regimes. Okay. Unfortunately, we can't do anything more using the definitive test. What if you take this option? Let me first select Manhattan. Yeah. So what I'm doing is a dummy is created for them. So a variable is created that which is equal to 1 for this region and 0 for the others. And this dummy is called, the default name is space. And you can see that this dummy is statistically significant over here. So this equation is you're regressing rent on this dummy and an interceptor. What you get is normally the rent is 1055. You can see over here 1055, and the difference in rent is 1233. So if you add 1233 to 1055, you'll get 2288. So this is all we can get from a cross-section data. But if we had panel data, then it would give us a difference in difference regression model. We can save the dummy over here. So if you click it, a dummy will be created. But basically what happens is you have a separate region for this. You have a separate data set. Okay. Any questions? Any clarifications or want to know certain additional issues? So the next test, what we are going to do is we are going to use scatter plots, and scatter plots are given over here, just to the right of the box plots. The basic concept of a scatter plot, I mean, this is something that we are going to use. Sorry, there's a typo over here. So in this regression, I have not written the error term. So, and by the way, this regression model that I'm doing is a time series data. It's not spatial. So we have a time series data set from 2000 to 2024. Let's assume that it's the growth rate of the Indian economy, and 2016 possibly created a structural break when we had demonetization. So how can you capture this? The relation between growth rate and some variable x is given by beta till 2016. After 2016, after demonetization, the relation between y and x has changed. That is our hypothesis. So what we want to find out is whether beta and delta are significantly different. So in other words, if there's no structural break, beta and delta are more or less same, then this would be the regression line. But if there's a structural break, then the slope of the regression line is going to change. Actually, it can be the intercept only. So what you have is a shift like this. If it is just the intercept, sorry, it should be a straight line. It will just shift upwards parallel. Here, it's changing. So the intercept is over here. So over here, we can see both the slope and intercept are changing. But it's also possible to think of a model where only the intercept changes. So a Chow test tells us, helps to determine whether whether there's a structural break. We estimate the two regressions separately, and the null hypothesis is there's no structural break. In other words, beta is equal to delta, and alternative is there's a structural break. So the test statistic is given by as follows, based on the residual sum of squares. This tells us whether, in a time series model, it tells us whether there's a structural break or not. So this is something that if you have done a course in econometrics, advanced course in econometrics, you should know this course, not advanced, intermediate course. Now, how do we do this in Geoda? So if you click on the box that I showed you, so this one, then you're going to get this window, and you should select, actually I think this borrow for the independent variable x and rent for 2008. You're basically saying that the rent depends upon the location, which is given by borrow. And if you click OK, you're going to get this regression. So basically, rent is being regressed on borrow. You have the different scatter points, and this is the best linear fit. So number of observations, 55. R square is pretty low. This is the intercept, you can see, and the standard error and t statistics. And this is the slope. So the slope has the coefficient is 0.923, And you can see it's uh, not significantly different from zero, fairly flat. So over here, we haven't selected any points. That is why we are getting only one regression now. Now let us brush. As soon as we brush, the selected area is given by red, and we have the blue area. The blue regression line, which is the unselected area. So we have three regressions. This purple is for the total, red is for selected. You can see over here 31 borrows have been selected, and the coefficient slope is minus 0.009. The blue for the unselected regions, 24 borrows, and the slope is 0.284. And the chow test result is given in the last line. The F value is 4.46 with a p value of 0.02. So we reject the null hypothesis at 1% level, which implies that there is a structural break. We can also select non-contiguous areas. So over here, I brushed this scatter plot. I selected these, how many? 3, 4, 5, 6, 7. I selected these. Actually, there are 8 points. The 8 points over here. There's another point over here. This is Manhattan and plus these 2 borrows. So you can see that this is the slope of the selected regions. Pretty sharp slope, 8.826. And this is the blue one is for the unselected region, 47 borrows. The coefficient is 0.590. And over here you can see F, and you can see that even at 1% level, we can't accept the null hypothesis. So clearly, this region, what we have selected, comprises a spatial regime. It's different from the remaining regions. On the other hand, if I select this part, so it includes Manhattan, part of Manhattan, but also some very low rental area, New Jersey. This is New Jersey. So if I select them, I can see that this is the slope of beta 0.08 minus 0.835 and 1.312. The F value falls 1.3. The P value is above 0.10. So now we accept the null hypothesis. Okay. So this is how we detect a spatial regimes. Let us go back to this NYC data. This is the scatter plot. Borrow, and now I have to select rent. Rent 0.8, clicking OK. Let me increase the size. So you can see this is the line for the entire data. And now let me select Manhattan. Huge difference. Look at the slope, 65, and unselected 0.370. And if the value is 60.81, p value 0. So it's not possible to accept the null hypothesis. On the other hand, well, this is very low rental value, but let us combine Manhattan and this value. Well, the p value rises to 0.26. So the null hypothesis is accepted. We don't have any structural break. So if I want, I could select, let me do something out. I want to select these points. Huge difference. Look at 60. Suppose I select only these points. Well, parallel. So not surprisingly, the p-value falls to 0.3849. So just do some checking. Over here, you can see the two slopes are different, but structural break, no. The structural break assumption, we cannot accept the structural break. So any questions? So, okay, what we have done is we have identified, we have found out that New York City comprises of, is not homogeneous, but heterogeneous. The rental value varies from one region to another, and we have clusters. So how do we analyze this using a regression model? See, when we are doing spatial analysis, there are two dimensions which are very important in spatial analysis, which are incorporated in regression model. The first dimension is spatial dependence. The value of y in one region depends upon the value in the neighbors. So the main focus has been on spatial dependence, and it can be captured very nicely using the spatial autoregressive component. It is also captured through the spatial error model, where the spatial dependence is captured in a different way. The reasons for dependence is different. Spatial heterogeneity, on the other hand, is, as I've said before at the start of the lecture, spatial heterogeneity is a situation when the relation between y and x changes between clusters, not between regions, but between clusters. Well, at the start, let us assume that it varies across regions. Towards the end of the earlier century, Fotheringham 97, Lloyd, current century 2010, these people started renew the focus on local aspects in quantitative geography. So unlike global Moranzai, unlike Salma models, which focuses on a global which has a global perspective, Fotheringham and his colleagues turned the attention on the local context. So they start from they focus on different units or clusters. So here we can make two distinctions. We can take a look at spatial heterogeneity in a discrete context and in a continuous context. In a continuous approach, the regression model coefficients are going to vary smoothly over locations, either deterministically or in a random fashion. And this is modeled using a geographically weighted regression. On the other hand, if we have discrete heterogeneity, we have spatial regimes. So what happens is, within a particular cluster of regions, the association between y and x remains same. So the coefficients, the intercepts are all going to remain same. Once we move from this cluster to another cluster, the association of the causal relation between y and x changes, and we end up with a different regression model. So that means spatial regime models are suitable when the relation between y and x varies across the system. So heterogeneity may be present either in the form of different intercepts, or both intercept and slopes are different. And just as in the time series data regression model, it is referred to as structural instability or structural change. And in terms of the regression model, it is expressed in the form of what we call switching regression models. So we have different regression models for each clusters. So basically, instead in time, we had clusters based on time periods. In the spatial context, we have location, a cluster of regions located in the same neighborhood. That is the only difference between a spatial regime model and the time series model, which we had looked at earlier. So models of spatial regimes are implemented or estimated by jointly estimating the coefficients of all predefined spatial regimes. So we form the spatial regimes keeping in mind certain restrictions. Each location has to fall in one cluster or regime, and you cannot have overlaps. A cluster cannot have non-zero value. A regime cannot have non-zero locations. There has to be at least one point, and each point falls into one and only one cluster. So let us suppose that you have m number of regimes, and you have got, let us say for simplicity, you have got only one explanatory variable. So you have y and you have just x1. What we do is, this x1 is transformed into a number of variables. So x1 is nominally a column, a single column. But what we do is we convert it into m columns. How is the m column forms? Let me just show this. Let me show this using Excel. So let us suppose that we have got three regimes, and this is your x. So we have got three regimes. So what we do is we make it x1, x2, and x3. So regime 1, I copy all the data. Regime 2, this is the data. Regime 3, this is the data. And it is 0 for the remaining part. So this is the mother variable. And we convert it into as many variables as their regions. So if you have 5 regimes, we will convert it into 5 variables. If you have 10 regimes, 10 variables will be created. Okay, is it clear, everyone? So the structural form is given by Yij. I is the region and J is the regime. So if we consider the child data for India, I will be the districts, and it is divided into 6 clusters. So J will be 1, 2, 3. J will be the clusters. So we have the intercept. So the same number of intercepts as number of regimes. X beta. Again, you can see beta is a vector. But how many vectors? It depends on the number of regimes. So basically, for every regime or for every cluster, we have a separate regression model. Okay, so each regime should comprise of a subset of observations, and each observation belongs to one and only one regime. So there will be no empty or null clusters. Now, in the simplest specification, as I said, only the intercept varies. This is referred to as a cross-sectional spatial fixed effects. But the more complex models, the more general models, the beta is also allowed to vary. So every regime will have the own intercept and own set of beta. The beta vector and alpha intercept will vary between across regions. So the regimes can be made up either of spatially contiguous observations, neighboring regions, or regions having a common characteristic but which are not neighbored. Now, what about the variance term, the error term? Well, the standard assumption in SALMA is, in the spatial model, is that the variance is constant. But if you have spatial regimes, a more realistic assumption would be that the variance is different for each regime, but within a regime, it is constant. So if you have 6 regimes, you will have 6 sigma squares. The variance will be, let us say, 2.1 for the first regime, 3.2 for another regime, and so on. This is called group-wise heteroscedasticity. And when we have group-wise heteroscedasticity, it basically implies you have different regressions for each group. So this is the standard approach that we follow when we want to test for structural stability in a model, just as the Chow test did. The only difference between the time series is, instead of time, the break is across or over space. But so far as the econometric treatment is concerned, it is the same as in the time series Chow test. The only problem is when the SARMA model, either the SAR model autoregressive component comes in, or the spatial error component comes in, or the SARMA. So you have both autoregressive component and you also have the error component, spatial error component. So when you have it becomes a spatial regression, then it becomes more complicated. Both estimation and specification testing will become more complicated. But if it is an OLS, we can just run it and apply the Chow restrictor. Okay. So the null hypothesis is that beta 1 across, we have m regimes, and beta 1 is equal to beta 2 and so on. In case of spatial models, we have an autoregressive parameter. So lambda. So lambda is, we assume that lambda doesn't change. So spatial dependence is constant if we have spatial heterogeneity. Similarly, mu, the autoregressive error term, that also is constant if we estimate a spatial regime 1. So if we have spatial heterogeneity, spatial dependence is assumed to be same for the entire region. Spatial heterogeneity is manifested only in the relation between y and x. Is this part clear? Or will I repeat it?
Clear, sir.
So generally, what we do is we first identify the different regions. We can do it in two ways. One is we can use the district codes. In New York City, for instance, it will be the pin codes. In the child data, it will be the administrative aerial units. And or what we can do is, this is one method. The other method is we can use different types of clustering techniques. So it's the identification of spatial regimes can be data driven. We then estimate models using based for each of the clusters. Now, if you're adopting the first approach, so you're delineating regimes based on some exogenous classification. This is ad hoc or arbitrary. But you can also form regimes using the data, analyzing the data. So the formation of clusters may be data driven, where we use clustering methods. Now the spatial clustering methods can be of different types. One is partition clustering. Actually, I will not be discussing clustering methods because that itself will take about 10 classes. Even if I focus on 4 or 5 of the main parts, each of them will take at least one class. So I'll just briefly discuss the main forms of clustering, and then I'll go to an example. So the segregation of the data points into non-overlapping. In partition clustering, the data points are segregated into clusters which are non-overlapping, and each data point is in exactly one subset. So a data point cannot be in two different subsets. So partition clustering can be of 3 types: k-means clustering, k-medoids clustering, and Clara. K-means clustering is it's a partitioning method. Based on the attributes, you simply divide up the regions. It's the simplest form of clustering. So basically what you do is you try to draw lines which will divide them into different clusters. Medoid. A medoid is a point in the cluster that is minimum similarities with all other points in the cluster. So I don't know whether it is visible, but over here, you can see over here, you have two medoids. So you have a medoid for cluster 1, you have another medoid for cluster 2. And once you have the medoid, all the points which are close or not dissimilar from over here comprise cluster 1, and we form cluster 2 in the same way. So the medoid approach is extended if you want to go for cluster, Clara. Instead of finding medoids for the entire data set, what Clara does, it takes small subsets of data and identifies the medoids over there. So you start off with a huge number of medoids. Then it tries reducing the number of medoids. So the number of clusters are reduced so that you're maximizing the difference between clusters. The second clustering method is hierarchical clustering. So this basically uses dendrograms, and again you have two approaches. So you can start off with assuming that all the units are separate, and you try to club together two units at a time. So you form clusters, small clusters, then you again combine the clusters till you reach the optimal number of clusters. So this is a bottom-up approach. You move from down to up. And derisive, you assume that there's no cluster and you start forming clusters. And again, you end up at an appropriate level of clusters. So somewhere in between. In fuzzy clustering, the main difference from partitioning is that the same data point can be classified into more than one cluster. So it's very good for if you're trying to use satellite imagery, because it's not so precise. It's not very clear whether in which cluster the point falls in. So you can see some examples where it's difficult to identify, and at the edges, the distinction blurs. Density based, we try to form clusters of high density vis-a-vis clusters of low density. So over here you can see this is a very high density, this is another high density, but these are low density. So this is known as DB scan, density based spatial clustering with application of noise. A modification or improvement is also there. It's called the HDB scan. Other methods, Geoda will allow you to cluster using machine learning process. So the automatic zonal processing, EZP, or the max-peak clustering. These are machine learning where you have to go for supervised, unsupervised processes. I'm not going into them. And next is we have got scatter, which is a spatial cluster analysis by tree edge removal. So basically you form a connectivity graph and then you start pruning the nodes. So as I've said, I'm not going into clusters, but let's have a look at the data. What sort of results will we get if we estimate spatial regime models? So this is a OLS, and this is New York City, where we are regressing rent on household size. For his is the, remember, it will be the proportion of Hispanic population, and year whom is the, I don't remember what it is exactly, but I think it's the average age of the neighborhood. So you can see that we get a regression model, and only household size is statistically significant. Minus, the t value is -6. In the other cases, the t values are below 1. So, well, actually, I'm just showing it to you, so we are not getting good results. What we see is the Lagrange, the lag, and error are both accepted. But if you go to the robust, both lag and error are rejected. So, well, this makes a bit of a problem. What sort of model should we choose? But let's go with just a regime model. Sorry, this is a spatial lag model. So if we estimate a spatial lag model, so this is not spatial regimes, just a lag model. We get W red. This is the neighborhood or spatial dependence effect. And this is the effect for the other variables. And you can see only household size is statistically significant. Now we introduce regimes. So just have a look over here. How many variables do you have? You have got 3 x's. This is the autoregressive term. This is the intercept. Now look over here carefully. We have the constant term. Let me change this. We have the constant term. And the 3 explanatory variables. So this comprises to regime 0. So we have taken the Manhattan region. This is the results for regime 1, Manhattan. W, however, lambda W, however, you can see is constant across the 2 regimes. So if you remember, I told you that the autoregressive terms does not vary across regimes. It is assumed to be constant. You also get a test of structural stability, the global test, this one. You can see that the null hypothesis is rejected. So the null hypothesis was there is no structural instability. So we can see that there is structural instability. And over here we have test for each of the coefficients. So you can see for the coefficients also, you don't have structural stability. This is the error model without regimes. So this is lambda. Again, when we estimate this, it is reported, I don't know why, in as 2 sets. You can see all of them are 0. Sorry, I made a mistake. This lambda, however, will change. So autoregressive term will not change, but lambda can change over here. And again, we have the Chow test of structural stability. So we do have regimes. But when we come to coefficients, we can see that here home and lambda. The slope actually doesn't change significantly. Okay, so this is a much more complex data set that we are going to use. The one that I sent you today. The dependent variable is a variable called price. Actually, these spatial regimes were developed in the context of hedonic markets, housing markets. So what happens is the price is taken, is the dependent variable. We actually take the log of price, and we also take the number of different dependent variables. Two things that we have to do. So one is that we have to take the log form of price. Second, we have to calculate age based on when the building was built. And secondly, we need the square of age. So this is the OLS. You can see most of them are statistically significant. But let's go to the data set and let's see what the results are. So I'm closing New York, and remember, I haven't done any clustering over there. So for clustering, you have to use Geoda, but after you have clustered or after you have created the variables, you can move to Geoda space. Remember, Geoda space does not allow you to create variables. You have to work with your pre-existing variables. So let me open the Kings County. This is point data. So you can see that I have created this variable log of price. I've also created age and age square. But I would suggest that you drop these three variables and try to create it yourself. Can you tell me how to create take the log of price?
Sir, can we do it from the calculator in the table?
Okay, so we go to table, calculator, then
What's the univariate?
very good. So we add a variable. Let's do it because we also need to. Let me drop these variables. All the variables that I painstakingly created. This is another variable that I created formed on clusters, but I'll keep it for that moment. Okay. So I go to table. There is calculator, univariate. So log 10 price, and I want it just before price. So I add it. Log base 10, and I choose price over here. So I'm applying, And you can see that the log of price is generated. How do we generate age of a building? Remember, we have the year of it was built, but it is in a different century. I want to find out what is the current age of the building in 2014. How do I do it? The age of the building is simply 2014 minus the year in which it was built. Right? Suppose the building was built in 1960. So 2014 minus 1960, how much is it? 54. So again, we create add variable. This is age. We want it before. Where is it? Year built. Sorry, it has to be bivariate. So it is 2014. I choose subtract and I choose year built. You can see over here. So I'm applying. And then I need another variable which is age square. This is age 2. Let us see, I want it before this. No, sorry, actually it has to be bivariate. So what we do is simply age, and this is multiply. We don't have power functions over here. So let's just check. So you can see over here age and age squared. Age squared has not been created. Let me do it again. Calculator. Oh, it should have been age 2. Sorry, I have to do it again, all over again. Subtract year built. Then I make it age 2. Age multiplied by age. I check this is age 2, so everything is fine. Let me check this. Yeah, so I've got age 2, and I've got date and log price. There's another variable which I have to create, which is calculator. This is special. So I enumerate. So I call this UI and I make it integer. I insert before. What does it do? You have integral values 1, 2, 3, 4, 5 like this. So everyone has a unique value. 21613. So now we have to create weights tools. UID, everything is same. So actually I had the file. Get an error message. Don't worry about it. So close it. Then we go to clusters and we go for the k-means. Actually, yeah, I may have some problems over here. If it closes, I have to do everything all over again. Actually, these clustering methods take up a lot of space and RAM. So it's not very easy. It takes a lot of time to run, particularly AZP, the machine learning methods, and even k-means, etc. The simpler methods seem to be a bit of a problem over here. But I hope I have the data. Okay, so the variables are there. I don't have to worry about them. I'm just loading the. So I'm not going to show you how to do the clustering because it's again going to hang up. So after we do the clustering, you can see the last variable. You have 5 clusters, 1, 2, 3, 4. So this, for instance, belongs to the first cluster. This belongs to the fourth cluster, and so on. Now let me open the file. So basically you have to open the file, create a weight file, and you have to run the clusters to form different regimes. So let me open the file, basic file. It's in King country, DBF. Let me open the weight file. It's over there. This is Y. So these are the variables that I've taken. I'm choosing the standard model, and I'm running this. So you can see the results. Actually, the problem with this data set is that it has got some inconsistent values. There are some outliers. So it should be cleaned before using it. But anyway, once we run it, we see that the error model is the appropriate model. So let's go for the error model, GMM. And this is the GMM. Just as we had done before. And you can see the last line. This is the lambda, which is for the error term. Now, this variable CL indicates the regime. I drag it over here, CL. Now, let me run the standard OLS model. See, regime 1. So this is, look at the number of observations, 5778. So we have the different results. This is regime 2, about 4,800 observations. These are the coefficients for, these are the results of the second model. This is regime 3. There were 5 regimes. This is regime 5. And for each regime, we have a set of factors. Then this is the Chow test. This is the Chow test. So the Chow test, first look at the global one. So the null hypothesis, structural stability, is rejected. And we can see by and large, see age. We have structural stability, these 4 variables, and this. These have structural stability, but bathrooms, bedrooms, condition, grade, the view, waterfront, these don't have structural stability. So the coefficient of some of the variables are changing across regimes. Okay. So we can go for an error model. Let me take a new model. It will be clearer. So again, you can see we have different regimes. But look over here. This is the error model. So the lambda is going to change. 0.39, 0.54, 0.46. And over here, structural stability, no. Lambda is not structurally stable. And the same assumption. I mean, the model, we have variation, we have spatial heterogeneity, except for some of the variables. Then next we go to, just for the heck of it, spatial lag model. A bit, I don't know why they do it, but it's like this. So this is the first result. And can you see the autoregressive term, there's no autoregressive term over here. So these twos indicate this is the second spatial model. For some reason, it is reported like this. And the autoregressive term is single. It's same across all models, all regimes. It's the coefficient is 0.266. And this is again this Chow test. So you can see that we don't have structural stability except for h square feet, and these three models. Okay. So in this way, you can run the Sarma model also. And you can get the results. Problem with the spatial heterogeneity model is we do see that the coefficients are changing, but the reason why this heterogeneity is occurring, that is not explained. We only know the structural instability, not its origin. But anyway, that is a step forward. And sometimes if spatial regression models don't work, then you can go for spatial regimes, and that can give good results. Okay, so I'll stop at this point. If you have any questions or you need some clarifications, otherwise I'll make some announcements and take a early break. Oh, Mohit is asking, is this regression discontinuity? No, regression discontinuity is something which is totally different. In regression discontinuity, what we do is, let us suppose that we are looking at the impact of a program on examining whether income increases as a result of this program. Now, the problem is if we take the program beneficiaries and compare them with program non-beneficiaries, there's a problem is that they may belong to two different categories. So suppose we have the program targets only beneficiaries. People who are below the poverty line. So in that case, we have on one hand, we have very poor persons who behave in a certain way, possibly whose education is quite low, who are not very advanced in other ways. And we have another group who are more educated, more affluent, greater access to loans. So in that case, comparison between these two groups will not be viable. The income difference between the two groups can be not only because of the program, but because of different characteristics, more education and so on. So regression discontinuity, what regression discontinuity does is, instead of looking at the entire sample, it simply looks at people who are just below the poverty line and people who are just above the poverty line. So it will be something like this. This is the regression line. And what regression discontinuity does is it looks at only this region. People only who are just below the poverty line, they are the treated group, they are the beneficiaries, and people just above the poverty line. So instead of looking at the entire sample, only a subsample which are fairly similar is considered. That is regression discontinuity. I would say that it is closer to, spatial regimes are closer to what we call interrupted time series. So, any other questions? Okay. So, attendance, Govinanda Mullik,